Okay, so this is a second step for studying application of a numerical method to gauge gravity duality. And this part apparently has a big overlap with Simon's lectures. But still, there are a few good reasons to this part, explain it, because hearing similar talk from slightly different point of view is always useful. And I think I will spend more time for non-lattice approaches, so it can be complementary. And first, warm-up example, which is useful for understanding why special care is needed for studying supersymmetric theory. It's actually usual pure Yang-Mills theory. It's just a bosonic theory, which does not have anything to do with the supersymmetry, but it's already actually very good instructive case. And let's start with Wilson's lattice gauge theory, which action is a coupling constant, which is actually inverse of two-fifth coupling, times n, times trace of so-called bracket. So unitary link variables, which is identified with exponential I times lattice spacing times gauge field, is living on links. And we just take product of link variables and take trace. And we sum up it with bracket actually is attached to each lattice site, and we just take sum with respect to site, which correspond to spatial integral. And coupling constant should be, in 4 dimension, this coupling constant should run as a function of lattice spacing. And then if we assume that I times A times A mu is sufficiently small, and expand this action around U equals to 1, then we get this Yang-Mills action in continuum up to higher order correction. And this is a simplest action we always use, but why do we have to use this action? The keyword is exact symmetries, and this action has several exact symmetry at the discretized level. So it has a gauge symmetry. This unitary, we can imagine a gauge transformation by omega of x. This is a unitary matrix living on each side. And for this link variable, we can perform a gauge transformation. So omega acts from left, omega dagger acts from right. And omega x is living on this point. Omega x plus mu is living on this point. And under this transformation, we have this u becomes omega u omega dagger. This u becomes omega u omega dagger. And u dagger becomes omega u dagger omega dagger, and so on. And we take trace. So omega and omega dagger here cancel. Omega and omega dagger here cancel. And omega and omega dagger, or omega and omega dagger here cancel. So this is invariant under this discretized version of gauge symmetry. And also this action has a 90-degree rotation by construction. It does not have continuum in rotation, but it has 90-degree rotation. And it has discrete translational symmetry. And it has a charge conjugation parity, and so on. And these symmetries are exact at discretized level. And when we take continuum limit, in which lattice spacing A is sent to 0, this limit should respect the exact symmetry at the discretized level. Then this exact symmetry guarantees gauge invariance, a translational invariance, rotational invariance, and so on in a continuum limit. But what happens if we don't keep those symmetries, especially gauge symmetry, explicitly in discretized level? For example, we can use shuffle momentum cutoff, which breaks gauge symmetry at the discretized level. But we can write down the action in a way that still it naively, at least the tree level, converges to correct gauge invariant action. But if we do that, okay, firstly, we are interested in low energy, long distance physics. So we integrate out high frequency mode and try to look long distance physics. But then because gauge symmetry is broken in a UV, gauge symmetry breaking radiative correction can appear. So even if we write down action which is correct at 3 level, radiative correction can completely screw up gauge symmetry. And here I just mentioned gauge symmetry, but if we don't have translational symmetry or rotational symmetry, then we may end up in a rotational non-invariant or translational non-invariant continuum limit. And to kill such radiative corrections, which we don't really want to have, one has to add counter terms to lattice action, whose quotient has to be fine-tuned. And in principle, we can do it. And if we can analytically calculate it, there's no problem. But in general, it's not an easy task. So this is a fine-tuning problem. And this is the reason why we must preserve symmetries exactly, at least partially. And that's the reason why we use Wilson's bracket action. And in super-MLs, so we want to keep gauge symmetry or other symmetry, especially supersymmetry, in order to control the radiative correction. But as Simon already mentioned, there is easy no-go theorem for lattice super-MLs, which is SUSY algebra already contains infinitesimal translation. And lattice breaks infinitesimal translation to discrete translation. So we don't really know how we can accommodate this algebra. We can keep such algebra on lattice. So if we can have discretized version of this algebra, it would be fine, but at least I don't know how to do that. And so it is impossible to keep all supercharges exactly on lattice. And then SUSY breaking radiative correction can appear in general. May or may not appear. But in general, there's no reason that such correction does not appear. But still, it is possible to preserve part of supercharges, so, part of this SUSY algebra, which do not contain translation. But then problem is whether such subalgebra is good enough to control radiative correction. And these three people, David Kaplan there, and Ami Katz, and Mita Tonzal. Oh, in this picture, so we went to Dead Sea together, and he thought that he has to read something, but he didn't have a book, so I just gave him Japanese book, and he's reading Japanese book here. If you can read Japanese, you can read Israel here. This is a travel guide. Anyways, so these three people gave a breakthrough idea. So as I said, it's possible to keep a few supercharges exact on lattice. And it's also possible to keep a few other symmetries, global symmetries. And then, as I said, the problem is if it's possible, it's good enough to control radiative correction. And they designed a good lattice SUSY theory, which keeps some of the symmetries of the continuum theory. And they show that at least in a lower dimensional case, such exact symmetry kept on lattice is good enough to control radiative correction. And Simon already spent substantial time about this approach, and also he will continue 2 more talks. So I don't go into the detail in this case. But in some cases, we can avoid fine-tuning problem by using lattice. But there are other approaches as well. So let me concentrate on these cases. And 0+1 dimension is particularly simple, because matrix quantum mechanics is UV finite. So we don't have to care about the radiative correction. Strictly speaking, finite radiative correction can appear. So sometimes finite counter term is needed, but typically, unless you take very stupid action, we don't need any fine-tuning. Even if we break symmetry, supersymmetry completely, typically in continuum limit, supersymmetry is automatically restored. And here I said 0+1 dimensional theory is particularly simple because of UV finiteness. And some people ask that For the maximally supersymmetric theory mills is also UV finite. Then why this argument does not apply in the case of 4D supermills? But the point is, in the case of the matrix model, in 0+1 dimension, this UV finiteness is not a consequence of cancellation. So bosonic part, fermionic part, each can be UV finite. But in the case of 4D theory, UV finiteness rely on cancellation in several different terms, contributions. And unless we can keep such a structure exactly on lattice, we cannot use this argument. So this argument does not apply to 4D supermills, at least naively. Anyways, because of this nice property, we don't even have to use lattice. For example, we can, as I will show in the next slide, it is sufficient to just fix a gauge and to introduce momentum cutoff. This works perfectly fine. And Simon and Toby show that lattice can also work. And actually, in this case, parallelization is easier compared to momentum cutoff. And recently, Kado and Kamata studied the supersymmetric lattice construction of 0+1 dimensional theory, though exact supersymmetry is not needed in order to get correct continuum limit. And as long as we compare their result at the finite cutoff level, and some recent work which actually took continuum limit using usual lattice action, it seems that with exact supersymmetry, convergence to continuum limit is much faster, at least for certain observables. So those exact SUSY is not really needed in 0+1 dimension if you just want the correct continuum limit. Still, using exact supersymmetric lattice may have some advantage. And I mentioned the momentum cutoff method. This is very simple. So in a matrix model, sorry, I forgot to write down action of a matrix model. But we can just, so that theory has a gauge field, scalar, and fermion. And so gauge, it's one-dimensional theory, so there is only one time component of gauge field. And actually we can fix a gauge completely by taking a static diagonal gauge. Okay, this beta is 1 over temperature, which is a circumference along compactified temporal direction. And we can take A0 to be static and diagonal, and the diagonal element is alpha over beta, and this alpha is between -pi and pi. We can take such a gauge. And then associated with this gauge fixing, we have to add Fateh-Popov term. But after that, we can just expand this x or fermion phi in Fourier mode, and we can just introduce cutoff. And this method completely breaks supersymmetry, but in continuum limit, rather supersymmetry is restored rather quickly, and we can numerically check it. And we can also use realtor naive lattice regularization. And this is actually the action we are using recently. Evan, Goro, Enrico Rinaldi are using. And this is just a gauge fixed version of the one used by Catero and Wiseman starting 2007. And we can just, so this is a ux u dagger minus x square. So this is a discretized version of the covariant derivative. And we have covariant derivative square. And this is just commutator term. And we have a fermion term, and this is Dirac operator. And it's really, literally very naive lattice regularization. It breaks supersymmetry completely. But as Simon and Toby had shown, in continuum limit, so this is restored. And we can also do order A improvement at tree level, by using a bit more complicated derivative for scalars and fermions. And it also works. And for example, we can take continuum limit. So this L is the number of lattice points along temporal direction. And we used so here we calculated the energy divided by n squared at n equals to 6 for SU16 theory at the temperature T equals to 1. And then naive action and improved action both converges to the same point. And of course, this plot alone does not show that we took correct continuum limit. But if so the supersymmetric non-supersymmetric lattice regularization can converge to wrong vacuum, there is no reason that extrapolated values should agree. But here we can see perfect agreement. And by looking at other quantities, we can show that SUSY is actually restored. And by using analytic argument Simon did, we can also show that SUSY is restored. So 0 plus 1 dimension is very easy. And there are pros and cons for several different regularizations. Momentum cutoff method is rather efficient, and it seems that at least compared to naive lattice regularization, restoration of SUSY is very fast. However, in a momentum basis, action becomes non-local. And so if you try to parallelize the code, actually lattice action is much easier. So that's the reason why at least I switched from momentum cutoff method to lattice recently. And the SUSY lattice is rather complicated, but appears to be efficient. And if we compare the plot of the energy as a function of temperature and the number of lattice points, so Kado and Kamata has a result from SUSY lattice, and we have results from naive lattice action. And it seems that, at least for energy, in their case, convergence is very fast. Strictly speaking, the action he used is Sugino's action, which is slightly different from Simon's. But anyway, even when we use Simon's action or David's action, I would expect the same is true here. And probably the reason is that, at least for the energy, cancellation between contribution from bosonic part and fermionic part is very important. And just one exact already guaranteed such a cancellation, and probably that is the reason. And for other observables, I don't really know. We should better check. So depending on your motivation, you can choose your favorite approach. And about 1 plus 1 dimension, Simon already gave a nice introduction and using lattice. But if we use lattice approach to 2-dimensional theory, probably we need fine-tuning. At least there is no proof that fine-tuning is not needed in this case. But if we don't use lattice, of course, that argument does not have to apply. And Maldacena, Sheikh Jabari, and Van Ramsdonk proposed the non-lattice regularization method for 3-dimensional theory. So they started with the so-called BMN matrix model. B is David sitting there, and which is a 1-parameter deformation of 0 plus 1 dimensional maximally supersymmetric animals. So original theory was this part plus fermion, and it has 16 supersymmetry, but they introduced 1 parameter mu. So there are 9 scalar fields, but and the original theory had SO9 symmetry. But they break SO9 to SO3 cross SO6. So X1, 2, 3 are, this indices ABC correspond to 1, 2, 3, and the small I correspond to 4 to 9. And they introduce such term. This epsilon is a structure constant of SU2. Epsilon 1, 2, 3 is plus 1. Epsilon 2, 1, 3 is minus 1, and so on. Okay, and they added mass term to X1 to 3, and for X4 to 9, they introduced slightly different mass term, and the fermionic term is also slightly modified. And there is good motivation to consider this theory from string theory point of view, but just as a gauge theory, if we look at this theory just as a gauge theory, interesting thing is this BMN model is not just, it's a 1-parameter deformation which keeps 16 supersymmetry. But here, SUSY transformation is also slightly modified related to this deformation. So this is supersymmetric deformation. And if you look at the equation of motion, we can easily show that this theory has fuzzy sphere solution. Okay, so here, this is the equation of motion. And here what I did was I set fermion to be 0. And I also set the x4 to x9 to be 0. And I assumed the gauge field to be 0. And took x1 to 3 to be constant. Okay, and then equation of motion become like this. Okay, so this term comes from this. And these two terms leads to this term and this term. Okay, this is the equation of motion. And then if you take our x to be SU2 generator, which satisfies this commutation relation, times some constant, then actually this equation of motion can be satisfied. So here, so if you take a commutator of Jx and J1 and J2, you get J3, right? And if this A is 1, if you take commutator of J1 and J2, you get J3. And if you take commutator of J3 and J2, you get J1. In this way, this part is actually proportional to JA, if you take this ansatz. And epsilon A, B, C. So if this is A is 1, B and C are 2 and 3, but B and C are anti-symmetric. So this part is actually, you can just write it as a half of a commutator of XB and XC. But then this part is again proportional to XA. And of course, this part is just XA. And then if you tune overall factor, you can satisfy this equation of motion. And we can see that this solution actually preserves all 16 supersymmetry. And so this is BPS solution. This is stable. And this is stable even after taking into account quantum correction. And this is so-called fuzzy sphere solution. And around it, we can obtain 2+1 dimensional non-commutative space. In string theory language, it's a so-called Meyer's effect. You can imagine that out of several D0 branes, from several D0 branes, you can construct fuzzy version of D2 brane. And so, in some sense, lattice, or two-dimensional lattice, is embedded in matrices like this. And the Lagrange limit and the continuum limit are related. And if you know about the non-commutative space, for example, Tony Gonzalez Arroyo is the expert about this. Actually, I said Meyer's effect, but how to get non-commutative space from this fuzzy sphere is essentially the same as getting a non-commutative space from fuzzy torus. And fuzzy torus is actually introduced in completely different context in so-called twisted George-Kawai model. So if you are interested, if you ask Tony Gonzalez Arroyo, he can explain it spending, I don't know, day or two. He never stops talking about this, I think. And anyways, but this formulation itself was invented in completely different context. But actually, after long wind and twist, it turned out it's very useful for defining supersymmetric theory. And if you know about the non-commutative space, actually, quantum field theory in non-commutative space is rather non-trivial. And at classical level, if you take commutative limit of non-commutative space, of course, you just get a commutative space. And the quantum field theory on non-commutative space reduces to, classical field theory on non-commutative space reduces to classical theory in commutative space. But if you take into account radiative correction, there is a so-called UV-IR mixing problem. And commutative limit is not really smooth. And in general, you end up in different theory. But with maximal supersymmetry, this UV-IR mixing problem does not exist. UV-IR mixing means in usual quantum field theory in commutative space, there is a divergence in UV. And that UV divergence is transferred to some strange IR singularity when we have non-commutativity. But maximally supersymmetric theory is UV finite. So nothing is transferred to IR. So when we consider maximally supersymmetric theory, there is no such a problem. So we can use this fuzzy sphere method to define, to obtain correct theory. So if you want to apply this theory, this method to for the n equals to 1 or n equals to 2, in general, you have to be careful about UVR mixing. You may or may not be able to get right theory you want. Anyways, and so I say the lattice structure of 2 dimension is encoded in 2-dimensional theory. But in general, here equation of motion just have to satisfy this commutation relation. And you can take any representation of SU2 algebra. It can be reducible or irreducible or whatever. And if you take spin S representation, the spin S representation is 2S plus 1 times 2S plus 1 matrix. And then you can intuitively, you can make spherical lattice consisting of this many points. And if you prepare k copies of spin S representation, then you have a matrix of the size 2S plus 1 times k. So you have something like x equals to be this factor times j of S tensor 1k, which is like j. So you have a block diagonal structure, and you have k copies. Okay, then it corresponds to k coincident D2 branes. So you can get the UK gauge theory in non-commutative 2-dimensional space. And the continuum limit corresponds to S goes to infinity of fixed k. And that limit corresponds to 3-dimensional elements. Strictly speaking, we have to tune S and also this parameter mu in a proper way. So we have to take a double scaling limit. But anyway, so in the Mardasana and Sheikh Jabari Van Ramsdonk paper, they show that what kind of double scaling limit should be taken. So we can construct 3-dimensional elements on 2 sphere this way. And if you look at their paper, they show how to take a large volume limit as well. And in string theory language, this describes a k coincident D2 brane or M2 brane, depending on the coupling constant. And it's also possible to take fixed S, large k limit. And they conjecture that this should actually correspond to 6-dimensional superconformal theory, which describes M5 brane and then S5 brane. And I think maybe Goro will give a talk related to this. Or maybe, yes, so he will give a talk related to this subject. So it's, they claim that just from a matrix model, we can somehow embed 5-dimensional lattice structure, keeping supersymmetry to matrix entries, and we can make very non-trivial superconformal theory. And their numerical simulation hasn't been done yet, but using so-called supersymmetric localization method, Goro and collaborators got good evidence for this conjecture. And the 3+1 dimensional theory is more non-trivial, and I assume Simon will explain. It's working now. Simon, yeah, but probably even without mic, my voice is loud enough. But for recording, they need mic, I think. So 4-dimensional theory is more non-trivial, and Simon will spend one lecture or two to this subject, I think. And 4-dimensional n equals to 1 pure supermills is special. And in this case, the field in the theory is just a gauge field and gaugino. And the only dangerous radiative correction comes from gaugino mass. But even if we don't have SUSY exactly on lattice, if we can somehow keep chiral symmetry on lattice, that can forbid mass of gaugino, and we can take correct supersymmetric continuum limit. And I think this is David's paper when he was a student. And I guess one of the reasons he wanted to define color symmetry on lattice is related to this paper, I think. Maybe we can ask him about it later. And, but this approach does not work for DNA equals to 4. But we can again have a hybrid formulation using lattice plus fuzzy sphere. I don't explain the detail here, but as Simon already explained, in 2-dimension, lattice formulation can perfectly work without any fine-tuning. And we can find such deformation of a 2-dimensional theory, which actually we cannot really keep all 16 supersymmetries, but we can keep 12 supersymmetries if we introduce similar deformation to 2-dimensional theory. And such 2-dimensional theory can be discretized in almost in the same manner by using an argument like Kaplan-Katz-Unzald or Simon or Sugino's. Then, so first we can have a 2-dimensional continuum theory with the flux deformation, with deformation term. Such theory can be defined by using lattice. But then additional 2-dimension is embedded in matrix degrees of freedom, so we can take Radian limit later. Then, yeah, from 0 plus 1-dimensional theory, we could get 3-dimensional theory. In the same manner, from 2-dimensional theory, we can get 4-dimensional theory. And at least toward the imperturbation theory, we can say that fine-tuning is not needed. And Goro and collaborators wrote a nice paper about application of the so-called Radian Eguchi-Kawai reduction to 4DNA equals to 4 supersymmetric MLs. This approach works only for Radian, but at Radian, in a rather similar manner, that is spatial structure can be embedded in matrix degrees of freedom. And again, here we don't really use lattice, so lattice no-go theorem does not apply. And the starting point is just this BMN matrix model. And they consider different kind of fuzzy sphere vacuum. And then they show that in certain Radian limit, Radian and small mu limit, correct continuum limit is reproduced. And if you use lattice approach, we need fine-tuning. But these people are trying to actually fine-tune the parameters. And so how many fine-tunings are needed? Probably 3-parameter fine-tuning. And it may be doable. And in this case, so these people are already doing simulation, and there are several interesting results. And I myself think these approaches are more promising, but because we haven't even done a simulation yet, I cannot say anything strong at this moment. I think it's important to pursue both directions. And I still have 30 minutes, so probably I should go to the third part. It's too early to stop, right? Okay, let's go to application to gauge gravity duality. And I have, for tomorrow I can add a few more slides tonight. I can just skip my beer. Anyway, so we want to apply such method to gauge gravity duality. And I already showed this plot in the motivation part. Okay, so we want to solve this theory numerically. And so I just said fine-tuning problem can be avoided. And in the case of 0 plus 1 dimension, it's particularly easy. For example, and also for 2-dimensional theory, starting with Cohen, Kaplan, Katz-Unzald, Sugino or Cottrell, these people contributed. And theoretically, it's at least to order perturbation, fine-tuning is not needed. And there are several simulation results available. And it seems that even at the non-perturbative level, fine-tuning is not needed at all. And in 3-dimensional, 4-dimensional fine-tuning, free formulations are proposed. And also, as Simon probably will explain, maybe even with fine-tuning, we may be able to study such theory. And one dimension is particularly simple. And I will explain later, but same problem actually exists in this theory, but at least in one dimension and two dimension, at least numerically, it's really possible that same problem is not really a problem. So, these two also big problem which prevented us to study supersymmetric theory for a long time. I think it's fair to say it's practically solved for many important theories. So we study the simplest case, p equals to 0. Okay. And so this is the Lagrangian. So we have 9 matrices, n by n matrices, bosonic matrices, and 16 fermionic matrices. And this is dimensional reduction of 4n equals to 4, or equivalent to 10 dimensional equals to 1. And it's due out to type 2A black zero brane near two-foot limit. And two-foot coupling lambda is defined by g amid square times n. And this coupling has dimension of mass cube. This is the biggest difference from four-dimensional theory. And any dimensional full parameter should be measured in the unit of this quantity. So this plays a role of lambda QCD, if you are familiar to QCD. And by two-foot limit, we mean this lambda is n to the 0, t is n to the 0, while e is n squared. This is typical choice. But more strictly speaking, as I said, any quantity should be measured in unit of this lambda. So strictly speaking, this dimensionless combination of temperature and coupling constant should be fixed to be order 1. And then energy scales like n squared. And if you want to measure correlation function, you should fix distance in unit of this lambda is fixed to be order n to the 0. That is two-foot limit. And for simplicity, very often we just say, okay, we choose lambda to be 1, and we just write t, but secretly it means this dimensionless combination. Okay. And because coupling has dimension, we cannot really have naive dimensional counting. Energy is identified to black hole mass, if the duality is correct. And we can calculate energy from a gravity side and the gauge theory side. And we want to see that they actually agree. And this is a prediction from gravity side. But this E is actually this combination. This T is actually this combination. And both are dimensionless. So it can have a strange power. And this is a prediction from gravity. If it was just a dimensional counting, E should be T, but such dimensional counting doesn't work. And 7.4 and also these numbers are analytically calculable. And B and C are in principle analytically calculable if we know all the details about stringy correction. But such calculation in gravity side is very hard. And these numbers hasn't been derived yet. And order 1 over n squared part is a correction from a virtual loop of strings. And we want to reproduce this result from gauge theory. Okay. And so this is a gravity prediction, but actually you can see that this is a supergravity part, and these are so-called string alpha prime correction. And alpha prime is related to size of the string. So string is not point particle, so it has finite size. And the size of the string is roughly square root of alpha prime. Okay. And that effect appears as a higher power of temperature. And when temperature is small, such correction is small. And it's related to the fact that temperature actually makes sense as this combination. So if we take T to be small, this combination of course becomes small. But if we take this lambda to be large, this combination also becomes small. So low temperature and strong coupling are the same. And high temperature and weak coupling are the same. And very often we say gauge gravity duality relates strongly coupled Lagian mirrors to supergravity. Strongly coupled is low temperature. So in this case, we expect supergravity to be good description of gauge theory at low temperature and Lagian. So we expect this low temperature behavior. Okay. And at the high temperature, we can use perturbative argument in gauge theory side, and we can easily show that energy goes close to 6 times T. And we want to see how this behavior at high temperature and this behavior at low temperature are connected. But first, we have, I already said, sign problem and fine-tuning problem are solved. But actually, we have one more problem, so-called flat direction problem. So this was the action. And you can see this is kinetic term, this is potential term. And the potential term is commutator squared. So if matrices commute, there is no potential. And eigenvalue can become arbitrarily large. Very often, quantum correction lifts that flat direction. But with supersymmetry, this flat direction is not lifted. So this is a flat direction which exists even at quantum level. And it can make simulation very unstable. And actually, this is not a bug, and this is actually a feature of the theory. Intuitively, eigenvalue of a matrix correspond to position or location of the zero branes. And the off-diagonal element describes strings connecting the zero branes. So if we have bound state of eigenvalue, which are tightly bounded by strings between them, such object correspond to black hole. And matrix are fully non-commutative one, all n squared entries are excited. Oh, by the way, we have 9 matrices, so we cannot simultaneously diagonalize them. So you can diagonalize one of the matrices, but in general, you expect all n squared entries to be excited. And but we can also imagine gas of the zero branes. So the zero brane can be far separated. Then open string connecting between them are very long and heavy, so they cannot be excited. And the zero branes don't really interact with each other and just freely move around. Such gas is also allowed. And in matrix language, because no open strings are excited, it describes by diagonal configuration. And you can also imagine 2 black hole solutions, 3 black hole solutions, and so on. So this theory contains not just single black hole configuration, but various other state, like 2 black holes, 3 black hole, or gas. Everything is described by this theory. And when we talk about this duality, we are focusing on single black hole solution. So somehow we have to restrict the path integral in order to extract black hole state. If you just naively do path integral, partition function is simply divergent. So how can we do it? And we can easily see that if the duality is correct, first of all, in string theory side, if we take string coupling to be 0, this black hole is stable. And the string coupling GS corresponds to 1 over n in gauge theory side. So that means at large n, somehow black hole should become stable. And it can be understood very easily by just drawing a picture of black hole. Black hole is strings, d branes particles connected by strings. And if you have bound state of n d brane, then all diagonal elements are sitting close to each other, and off-diagonal elements are fully excited. And imagine, one of the particles is emitted. In this picture, this particle is sitting next, very close. But actually, this particle, because this size of the screen is not big enough, I put point here. But this point is actually very far from others. Okay. Then strings connecting this particle and others are very long and heavy and not excited. That would mean we should have such configuration. So this column and entry become just 0. Okay, because the strings are not excited at all. But then we only have n minus 1 squared plus 1 degrees of freedom. And once this particle escapes from others, it can go anywhere. But when it tries to escape from others, somehow many components has to become 0 simultaneously. And it's a very rare process. And such rare process is suppressed by entropic factor. And just counting the number of degrees of freedom, you can see that the suppression should be something like exponential minus n, because n component has to become simultaneously small. So entropy, roughly speaking, decreases 2n. So it has n squared entropy. This has n minus 1 squared entropy. Difference of entropy is n. Okay, and phase space volume is exponential of volume. So such configuration is factor exponential n, more likely than such configuration. So this is suppressed. And such suppression factor becomes very small when n becomes large. This is how at large n black hole becomes stable. And numerically, we can actually see that black hole becomes stable when n becomes large. So if you plot trace x squared divided by n, which characterizes the radial coordinate of the diagonal element, then as a Monte Carlo time, a function of Monte Carlo time, if you take, say, n equals to 4 and start with x equals to 0, then it increases and it becomes metastable, but then it diverges rather quickly. But if you increase n to be 8, then you have a bit more stable simulation here, but then eventually it diverges. But then if you increase n to 16, it can survive longer. And practically when n is big enough during your simulation, you never see such runaway behavior. Then you can just safely estimate expectation by various waves using such metastable configuration. I think this is a rather straightforward, rather, how to say, standard method to deal with metastable state. And I used this joke slide already several times, so one of the person at least knows what this plot means. But this plot is a plot of trace x squared as a function of Monte Carlo time. And so if this is black hole, this is this is black hole, this is the fluctuation. And this is a very famous plot, and he already knows the answer, so you shouldn't say anything. Do you know what is the meaning of this? Anyway, I asked him, but you can also answer. I think my collaborator already knows. So, yeah. So actually, this is a social experiment, and this is a stock price, a historical chart of stock price in Tokyo market and the New York market. So Bank of Japan detected flat direction here, and they completely killed it, and we are enjoying a very stable black hole phase. And the Federal Reserve Bank is not good enough, they're not good enough to kill flat direction. And recently it's going up high, it's 2015, but after like 50% increase by now. Okay, so we want to study this phase in order to test gauge gravity duality. But at the same time, this flat direction corresponds to evaporation of black hole. So this is actually even more interesting physics. So if you are interested in large n limit, this is the limit we want, the phase we want to study. But life in Japan and the States, they are interesting in a different manner. Anyways, so we want to see how they are connected. And so let me introduce some history. I think maybe I will spend all my slides today, so I have to work very hard tonight. So these two first simulations. And actually, even before this, there's some early attempt using some different method. Anyway, so in 2007, we tried the simulation. And if we go to low temperature, which is a strong coupling, we can show that the simulation result go close to black hole prediction. And this Simon and Toby did a similar simulation using different action. And in their case, rather than energy, they plotted energy divided by temperature. So y-axis is slightly different. And in this normalization at high temperature, energy should go close to 6 times T. In their case, they divided it by T, so it should go to 6. And you can see that at high temperature, this value actually converges to 6. And then if we go to low temperature, gradually flat direction sets in. And in this paper, they show that these are the good points, which do not detect the flat direction. And they also show the simulation point which picked up flat direction. So this plot already shows how problematic the flat direction is. It's not totally under control. Anyways, from this plot or from this plot, you should just forget about this point and just look at this point. And we can see that qualitatively it's good, but it's not good for any fit. We can see it's going close, but we cannot really see quantitatively claim that this low temperature behavior predicted from gravity is reproduced. We cannot do any numerical fit. And also, we didn't take large n. Our largest n was 14 at the time, and we didn't even take continuum limit. So in this lambda is the momentum cutoff. So lambda equals to 4, roughly speaking, correspond to 8 or 9 lattice points. And in their case, I forgot the number, but the number of lattice points is like 8. And so I would just say it was qualitatively good, but it was consistent with supergravity due to cutoff effect and large error, maybe. And then in 2008, we did beta simulation, and we could see that the actual simulation, these points obtained from simulation at slightly larger n and larger cutoff go very close to supergravity, and the difference could be explained as a stringy correction. But still, we didn't take large n continuum limit. But then 7 years later, Kado and Kamata did the beta simulation using supersymmetric lattice. And one of the reasons that the Kado and Kamata could do, better simulation using with larger n is that, of course, partly, after 7 years, better computer is available. But at the same time, I spent time to write a proposal for getting a simulation time for supercomputer. And Kado used it to trying to kill my report. Okay, so I get a supercomputer resource, and he spent it to challenge me. And they got this result, and the result looked pretty much close. But this is our fit result, and this is their fit result. So fit looks very different. And by the way, Philip O'Connor did a similar simulation in 2015. And if we plot, our result and the Kado Kamata result on top of each other, they are close, but different. And this tiny difference is already crucial, already fatal. We cannot really see which is correct. We need large n and continuum result. And we still have 15 minutes, so should I move on? Do you want me to work hard tonight? Okay.
My fault for not listening carefully. Go back to the matrix and explain the entropy factor of a single black hole versus the, this one, yeah.
Okay. So this is very rough argument.
Yeah, let me get the argument again, yeah.
Yeah. So very roughly speaking, so we have, so first of all, why flat direction can appear? Because once flat direction is xi, xj equals to 0. And this I and j run from 1 to 9. Okay, and such flat direction correspond to such configuration. But physically, the reason is that if you have d branes separated far away, then they can interact via off-diagonal element. Okay, and the bosonic mode gives attractive force, fermion gives repulsive force, and they cancel. Okay, and so that's the reason why particle can go very far. So if you have a bunch, black hole phase is bunch of n d branes, and if you look at the this commutator part, okay, so you can write this x to be
Sorry, this split where you only lose one d brane is not very dramatic, but
okay.
If you're to split n, let me just ask the question. If you split n to n over 2 and n over 2, then I can see an exponential difference. Is that what you're really trying to do?
So first imagine, so you have a bunch of n particles forming a black hole. And what you said is if it's split to 2 black holes. Okay. This is very dramatic, and of course, when we imagine black hole evaporation, we imagine particles emitted one by one. Okay, black hole does not split to 2. And in this case, you can easily see that suppression factor is actually exponential minus n squared. And the reason is, if you just count the number of degrees of freedom, okay, this matrix corresponds to n by n matrices. All entries are excited because diagonal elements are d branes, and off-diagonal elements are open strings. Because all d branes are sitting close to each other, all off-diagonal elements can be excited. And this configuration corresponds to such block diagonal configuration. So off-diagonal element in this block corresponds to string connecting these d branes. And the off-diagonal element in this block corresponds to strings connecting these d branes. But between here and here, no open string can be excited. So a lot of components has to become 0 simultaneously. But if only one d brane is emitted, then matrix configuration is this. So only n of the diagonal element has to become 0. That's very good. So here I say the phase space separation.
That's fine, but you can select anyone.
So if you do a picture of a phase space, it's more like, so it's a huge. So imagine this part of phase space corresponds to single black hole. And once particle is excited, it can go anywhere. So this part describes something like this configuration. But there's some bottleneck. So in order to, once d brane is emitted, it can go anywhere. But in order for such configuration to become such configuration, many configuration has to become small simultaneously. Such process is suppressed. So there's some bottleneck. And if you just compare this part and this part, so it's not qualitative and quantitative. I'm just making qualitative argument. Between here and here, there's this kind of suppression. But once you go, D-ray pass through this bottleneck and emit it, then it can go anywhere. So as you said, it picks up volume factor. And so it can go anywhere. This is flat direction. So flat direction exists. But overall n doesn't help compared to exponential suppression.